the southeast of England, engineers are building the UK's biggest and most technologically advanced railway. The Channel Tunnel rail link will carry 180-mile-an-hour trains from St Pancras in central London through the Channel Tunnel and on to Paris and Brussels. It's the first time a new railway line has been built in Britain for more than 100 years. It'll take about 5 years to complete and cost £5 billion. Here at Ebbsfleet, 20 miles east of central London, they're building the most complicated tunnel on the line, designed to take those trains at 180 miles an hour in a long, gentle S-curve under the Thames.
Our part of the project is what they call the Thames Tunnels, which basically consists of 800 meters of ramp structure on the south side of the river. Then you move into the tunnel. The tunnel is 2.5 kilometers long, and it's a twin-tube tunnel, i.e. one line going towards London and one line coming back from London. Our tunnel at the moment stands at about 900-meter length.
Building a tunnel to take high-speed trains is a highly specialised task.
The trains actually hurtle through here at 180 miles an hour. You can imagine this tunnel as a circular bore of a piston, and we've got a very large train. As it goes in at high speed, it acts like the piston in a car engine, compresses the air ahead of it and pushes the air out.
And that means the Thames Tunnel has to be the most aerodynamically precise tunnel in the world.
We've all been sitting on the trains as I've gone into the tunnel, and you get the cup of coffee and you get the shake and your ears pop. This is a very high-performance tunnel. We've got to make sure that the passengers have the same comfort criteria virtually as travelling in an aircraft.
And there are other very special challenges.
When we get to the deepest part of the tunnel under the Thames, we're actually going to be tunnelling under 4.5 bar of pressure.
Now, 4.5 bar water pressure means 45 meters of water above your head. And even in compact ground, with small fissures, you would get a huge ingress of water in that type of ground.
To solve these problems, the engineers have drawn on the lessons they learned on another, rather bigger tunnel just down the line.
One of the world's most famous tunnels lies right on our doorstep. The Channel Tunnel is the world's longest undersea crossing. It took 5 years to complete and cost £9 billion.
The Channel Tunnel is 31 miles long, with 22 miles of it lying 40 metres under the seabed. In 1987, the French started digging north from Calais, the British south from Folkestone. They met in the middle on December the 1st, 1990. Since it opened, 60 million people have passed through it. That's around 20,000 a day.
The dimension of the Channel Tunnel is quite unique. I think it's probably one of the biggest projects of all times.
But the world's greatest tunnel is altogether less well known. Most people have never heard of it. The Seikan in Japan beats the Channel Tunnel for length by just 2 miles, and it took a staggering 25 years to build. The 33-mile-long Seikan links Japan's northern island of Hokkaido with the Honshu mainland. Nearly half of it runs under the Tsugaru Strait. It was in these turbulent waters in 1954 that a typhoon sank 5 ferries, killing nearly 1,500 people. The subsequent public outcry led to the construction of the Seikan. Work began in 1964, with crews on the Honshu and Hokkaido sides digging 3 separate tunnels. First, they bored a pilot tunnel to survey the marine geology and the groundwater flow. Then, as they dug the service tunnel, they also dug galleries off to the side, which were used to construct the most challenging tunnel of all, the 3-story-high main train tunnel. But the most extraordinary feature of the Seikan is the way it was built. The Japanese were forced to use one of the most dangerous tunnelling methods of all, hand drills and dynamite.
When you get a tunnel that's extremely strong rock, the way that they would normally be done is drill and blast, where you typically drill a hole, put the explosives in, fire it, go in, clean it out, and continue round after round.
It's one of the earliest tunnelling methods, and it's fraught with danger. It was first used extensively on one of the world's most infamous digs, the excavation of the St. Gothard Tunnel, which runs through the Swiss Alps. At 9.5 miles long, this was the greatest engineering project of the late 1800s. The dig used all the high-tech tools of the day, including the 4-headed rock drill. Nearly everything went wrong. 600 metres in, the miners hit a water table that rushed into the tunnel at a rate of 14,000 litres a minute. Cave-ins and construction accidents were common. By the time it was completed in 1882, the St. Gothard had killed 310 men. It was an example of tunnelling at its most dangerous, and sadly, it was far from unique.
Tunnellers faced deadly danger. Epidemics were caused by stale air and contaminated water. Up to a quarter of the workers could expect a serious injury, and as many as 1 in 20 would die.
These days, safety regulations are stringent. Every man in the tunnel carries an identifying tag and emergency oxygen supply. Safety officers know at a glance who's in and who's out. It's a system that proved vital on the Seikan. As they struggled through one geological fault after another, the Seikan tunnellers pumped cement into the tunnel walls in an attempt to hold back the water. But the world's greatest tunnel was to come at a terrible price. In 1976, they hit a patch of soft rock. The water came flooding in at a rate of 80,000 litres a minute. Whole sections of tunnel representing years of work were lost, and it took 2 months just to control a flood. Finally, in 1985, the tunnellers broke through.
The most dramatic moment was the scene where the last wall was blown out and the wind from Hokkaido rushed through to the Honshu side.
5, 4, 3, 2, 1, attack!
The wall was exploded with dynamite. Then a light came through from far ahead into the pitch-dark tunnel. I realized that this moment was the result of all our efforts over the past 25 years.
The Japanese dug the Seikan the hard way. The tunnel killed 33 men, a toll that would be unacceptable now. But today's engineers have one big advantage, the ultimate in high technology, a giant machine that's changed the face of tunnelling forever. Building the world's greatest tunnels requires the world's greatest technology. And it doesn't come greater than this, a tunnel boring machine, known as a TBM.
TBMs have completely revolutionised tunnelling. They've more than halved the amount of men needed and drastically cut production time. On a good day, this huge wall will turn at up to 2.5 revs per minute, and these steel teeth can cut through 20 metres of earth.
TBMs are the ultimate in high-tech engineering. Behind the giant cutting face, an 80-metre-long train carries the machine's support equipment, a sophisticated computer control room, and the tunnel lining machine. A TBM is manufactured to order. It takes a year to build and costs around £6 million. At Ebbsfleet, east of London, they're using a TBM to dig and line the 1.5-mile Thames Tunnel, part of the Channel Tunnel rail link.
We advance the machine 1.5 metres, dig the ground away with the tunnelling machine. We then build a ring in the gap that's created. Once that ring is built, the machine then cuts the next 1.5 metres and it pushes itself off of the last ring that it's built. And then that is a repetitive cycle.
It takes 40 minutes to dig 1.5 metres and another 40 minutes to position the complete lining ring and bolt it together. But remember that 45 metres of water pushing down on the tunnel roof? Well, the engineers have an ingenious way of stopping it gushing in at the cutting face and flooding the tunnel.
We'll stop the River Thames from coming in because we actually fill the front of the chamber with a positive pressure of slurry. That slurry then gives some support to the face, and it's all sealed behind a bulkhead. So then as the cutting wheel excavates, the slurry's continually topped up to maintain a pressure.
It's an adaptation of a technique that's been around since the 1930s. In those days, the solution to water leakage was to pressurise the whole tunnel. Tunnellers then worked in compressed air, which held back the water. But it was a tricky technique. The air pressure had to exactly match the pressure of the water. Otherwise, the air pushed its way out and the water came in. But the real danger was a hidden one, and its effects were devastating.
When I worked in compressed air, even then they didn't have a lot of knowledge. Now they have a lot of information on it. Nitrogen bubbles get into your joints and so on. And I suffer some with that, a few aches and pains.
Like deep-sea divers, tunnellers suffered the bends. For many, the nitrogen bubbles in their joints crippled them for life. In a modern TBM, only specialised personnel are allowed to pass through the airlocks into the pressurised face, and even then, only to undertake essential repairs or maintenance. A TBM like they're using to dig the Thames Tunnel is warm, dry and well lit. It's an example of just how far tunnelling has come. But it's not always the tool of choice. Sometimes tunnellers still use old, traditional methods.
In fact, there's many techniques of tunneling, and there's many adaptations of different techniques depending on the type of geology that you are trying to tunnel through. So you cannot generally say that tunnel boring machines are used everywhere.
A few miles down the line from the Thames Tunnel, they've just finished the North Downs dig. Here, the tunnel face was literally scraped away and the walls sprayed with concrete. Still further down the line, another technique was used. A prefabricated tube was simply dropped into a trench and covered over. It's a method that was first developed for short river crossings. One of the world's earliest and greatest examples of immersed tube tunnelling lies under the waters of the Detroit River in Michigan. Built in the 1920s, the Detroit-Windsor Tunnel is a mile long and links America with Canada. 9 enormous steel tubes were assembled on dry land and sealed with temporary bulkheads. Each tube was 10 metres across and 75 metres long. The watertight tubes were pulled into the river and tugged into position over the trench. Divers then lowered them into place and bolted them together. Finally, the bulkheads were smashed through and the workers finished off the interior. They covered the walls by hand with more than 200,000 porcelain tiles. And they're still there today.
Immersed tube tunnelling is fast and cheap, but when the water is deep or the crossing is long, it becomes impractical, and there's no choice but to head for the ground under the riverbed.
The world's first tunnel dug under a riverbed lies beneath the Thames in central London. Built by Brunel between 1825 and 1843, the original Thames Tunnel now carries the London Underground's Eastern Line under the river between Rotherhithe and Wapping. It was an extraordinary feat of engineering, and to achieve it, Brunel invented the world's first tunnelling machine.
To start a tunnel, you have to get down, first of all, to the required depth. So Brunel came up with what was then a completely revolutionary idea to create a structure above ground, first of all, and then to sink it into the ground under its own weight by excavation below.
Brunel's tunnelling shield was dropped piece by piece into the shaft.
When it reached this point, finally, one was able to bring down the actual shield, which was a number of cast iron pieces, which were then assembled here at the bottom of this huge shaft, so that the construction could then start to excavate forwards into the tunnel for the first time.
36 men worked at the face, protected from collapse by the rectangular cast iron structure. As the men dug out the face, the shield was moved forward and the tunnel walls lined with brick. It was an extraordinary achievement and quickly established shield tunnelling as the method of choice for digging in soft earth. On this tunnel, built for the Ford Motor Company in 1930, workers had to cope with clay pouring into the shield at the rate of 2 tons a minute. The walls were then lined with steel ribs. The tunnel boring machine is simply a modern, high-tech equivalent of Brunel's shield. The only real difference is that the digging and lining is done largely by computers and hydraulics. But this doesn't diminish the challenge of tunnelling or make the work any less rewarding.
Well, the challenge of tunneling is that basically you never know what's coming within the next meter of where you're going, because it's virgin ground that you're in. I suppose that's the challenge of it. And that's the special part about it.
It's big engineering and it's complicated engineering, and it's the thing that the challenges you get with tunnels are never the same. My last tunnel was a NATAM tunnel, which is a different type of tunnel. This is a TBM tunnel. It's the variety, the complexity, and the challenges you face every day, basically.
For the dedicated tunneler, it seems there's really only one downside.
When you see a bridge, you can say, look, I built that bridge, whereas in a tunnel, all you see is a round little hole.
The Channel Tunnel Rail Link opens for business in 2006. It'll be the most advanced railway line ever built in Britain, and it will cut the journey time from London to Paris by 45 minutes, which will effectively make it faster than flying.
Tunnelling is one of the greatest engineering challenges on the planet. But as the population increases, land becomes more scarce and more valuable. So digging underground is fast becoming the preferred option. The lessons we've learned from the Channel Tunnel and from the Seikan in Japan have certainly made the work safer and less costly. But even greater challenges lie ahead. Plans are currently underway to drive a 40-mile tunnel under the Alps from Austria to Italy.
They put them up and then they knock them down. Next Monday at 8, we look at the world's greatest demolitions. Next tonight, Weapons of World War II sets its sights on the tank.